Well, here I am all by myself, but I decided to record some problems anyway. So this first problem, we're supposed to find the resonant frequency. So to find the resonant frequency, that would be where the imaginary part of the impedance is equal to 0. So we need to find the equivalent impedance of this circuit, and then from there find out where the imaginary part of that is equal to 0. So because I am terrible with calculations, it's easier for me to do this algebraically and then to plug in numbers at the end. And then not only that, at that point you'll have a formula that you can use for anytime you've got the same elements in the same configuration. So if I can get my window correct, does not look like I am capable of doing that. All right, so here I've got a resistor, an inductor, and a capacitor in parallel. So Z equivalent, or the impedance of the entire thing, is R in parallel with L in parallel with C. And so as an impedance, that's R in parallel with L J omega L in parallel with minus omega over JC. And that is, we could do them two at a time, R in parallel with J omega L in parallel with minus omega over JC. So R in parallel with J omega L, it's product over sum, so that's J omega L R over J omega L plus R. Now, when we get this, in order to find out where we have, I don't know why I wrote this here, minus J over omega C. Is the impedance of the capacitor. I guess I'm tired. You would want to have all of the imaginary stuff in the numerator in order to set it equal to 0. And so eventually we are going to have to rationalize it. So now we need to have these two in parallel. We'll have product over sum again. So that will be J omega L R times minus J over J omega L plus R times omega C over J omega L R over J omega L plus R plus minus J over omega C. Now, to do this, I'm going to multiply by the common denominator of the denominator. So the common denominator of these two in the denominator, omega C times J omega L plus R over omega C times J omega L plus R. Now the nice thing about that is in the numerator, that will cancel. Okay, I'm not sure, I'm editing this, so I'm going to go back to this part right here. So I'm multiplying through the denominator, so I get, in the numerator, the denominators cancel, and I get J, well, J times J is minus 1, but it's minus J squared, so that becomes plus 1, omega LR, and then the denominators cancel. And then when I multiply this term by this one, the J omega L plus R term cancels, and I have J omega L R times omega c minus j, and with this one the omega c term cancels, and I'll have times j omega L plus r. So then the denominator, well, I have omega LR in the numerator, and then in the denominator I have j omega squared RLC, and then minus j times j is minus j squared, which is minus 1, which is plus 1, so plus omega L, and then minus j times r is minus jr. Now I need to rationalize this, so I need to get the real part and the imaginary part of the denominator separated. So the real part is omega L, plus the imaginary part is j times omega squared RLC plus, minus r. And then I'll multiply this by the conjugate, so omega L minus j times omega squared RLC minus r over omega L minus j omega squared RLC minus r. And then I don't care about the denominator anymore because that cannot make it equal to 0, so I just care about the numerator. So if I distribute that, I get omega squared L squared r, which I don't really care about. It's only the imaginary part that I care about, minus j times omega LR times omega squared RLC minus r. And from this part I get, again, I don't care about the real part, I only want to make the imaginary part equal to 0. So I want to make omega LR times omega squared LRC minus r equal to 0. So from this first part I get the trivial answer, omega equals 0. So that's trivial resonance. So we don't care about that. Resonance. And from the second part I get omega squared RLC minus r equals 0. Omega squared RLC equals r. Omega squared equals r over LC. RLC. R's cancel. Omega equals 1 over the square root of LC. And that gets us the resonant frequency for parallel RLC. And then our particular problem had R is 1 kiloohm, doesn't matter, L is 10 millihenries, so omega equals 1 over the square root of 10 times 10 to the negative 3 times, capacitance is 10 nanofarads, so 10 times 10 to the negative 9. 1 over the square root of 10 times 10 is 100 times 10 to the negative 12. Or 1 over the square root of 10 to the negative 10, or 1 over 10 to the negative 5, or 10 to the 5th radians per second.